Uh, our today's lesson is about volume integral. As we discussed in our previous lectures, the line or the path integral in greater detail, and then we connected it with conservative and non-conservative forces. Now, this time we are going to discuss the volume integral. And in the volume integral, as it's clear from the name that we have to integrate for a volume. And we can do this for both a scalar function and a vector function. So for a scalar function like phi x, y, z, if we have this as a scalar function, then its volume integral is defined as phi xyz into dv. Now this dv is the volume element, and its value in rectangular coordinates is given by dx into dy into dz. So the volume element in the rectangular coordinates is given by dx, dy, dz. And if you put this scalar function here, and then you integrate over the whole volume, then you get the volume integral of this scalar function. So the volume element, this dv, is a scalar quantity, and this really makes the integration process really simple. We do not have to take any dot or cross um, to perform our integration, as we did in the previous case. Like for line integral, the line element was a vector quantity, and then uh, we have to use vector of vector function and dot and cross products. But here we are free from that. We do not have to use any dot or cross product because this line element is a scalar quantity. So for a scalar function, this is just a simple product and an integration over the volume. So now the integration over the volume is really three integrals. One integration over the dx, the x variable. The other integration is dy over the y variable, and the third integration is over the z variable. So we have to perform just only three integrations to get our volume integration. Um, Now this phi or this scalar function can be anything, like in physics. Um, in electrodynamics, it can be a charge density or charge per unit volume. So if this phi x, y, z, or phi may be a function of r in the spherical coordinates, then we can put this charge density over here in place of this phi. And then when we integrate over the whole volume, we will get the total charge for this special case, if this scalar function is its charge density. So this scalar function can be anything. And then if we integrate this over the volume, then we get a corresponding physical quantity. I'll discuss in the problem sections that what type of physical quantities can be obtained from volume integrations. Similarly, if we have a vector function v, x, y, z, or it can be in any coordinate system, then for a vector function, the volume integral is defined in a similar fashion. We do not have to use any dot or cross product. As I mentioned earlier, that this dv, the volume element is a scalar quantity, and then we do not need any dot or cross product. So just put the vector function or the vector point function and multiply it with the volume element, and then perform integrations. If dv is in dx and dy or dz are the rectangular coordinates, then you have to integrate with respect to x, with respect to y, and with respect to z. So indeed, this is a three times integration to get this whole volume integral. Now, the example of this vector quantity can be, for example, from fluid dynamics. If this rho is the mass density, mass per unit volume, and this v is the velocity of the fluid, then integrating these two over the whole volume will give us linear momentum of the fluid, because this is mass per unit volume and this is the velocity of the fluid. So integrating mass per unit volume over the volume will give us the total mass. Now total mass times the velocity is just the linear momentum. So this is just an example of a vector field integrated over a volume, and this is an example of a scalar field or a scalar quantity over a volume. So the volume element is a scalar quantity, and this makes the process really easy. Now, most of the time, or till now, we discussed our problems in rectangular coordinates. But sometimes, if we have spherical symmetry or cylindrical symmetry, so then it's better to use spherical or rectangular coordinates. We'll discuss this process in a greater detail in our upcoming lectures. But at the moment, let me just tell you that the volume element in the spherical coordinates is given by this expression, r square sine theta, dr, d theta, and d phi. Uh, we'll prove this result later in this course, but at the moment, just take it as it is, that this is the volume element in spherical coordinates, just like this is the volume element in rectangular coordinates. We will use this value in one of our examples or in our problems, and I'll explain that how do we get these quantities. So this is the value of the volume element in the spherical coordinates. uh, Geometrical meaning of the volume element, that what is dv uh, in rectangular coordinates and what's dv in spherical coordinates, or what what is its physical meaning, or what is its geometrical meaning. So for example, I have a box, like this big cube, this one, and I'm interested in finding its volume. Now this is a regular shape and its volume is simply mm, x times y times z. This is just the volume r. If this side is a, this side is b, and this side is c, then the volume will be just the product of these three sides, and this will be a, b, c. But uh, let me do this process with the help of the volume element. So suppose I have this big box, and um I want to find the volume of this box. I already know this, but I want to calculate this with by using this volume element thing. So for this purpose, consider a very small box of volume dV inside this bigger box. So this small box is having a volume dV, and if this is the x, if this is x direction, it is y direction, and that's, let's say, z direction. So if this length is dx, this length is dz, and this vertical length is dy, then the volume of this little box is given by dv, and this dv is what we call as the volume element. This is a small piece of volume taken inside this bigger box. So if so, the volume of this small box is given by this dv. If I want to find the volume of this bigger box, I have to integrate this thing. Like I have to integrate both sides. So integrating this side will give me dv, and I have to perform three integrations on the other side. One integration is with respect to x, the other with respect to y, and the other with respect to z. But I have to use appropriate limits. For example, the limit on the x may be, let's say, from 0 to 3 meters. For y, it will be from 0 to 5 meters, and from z, it will be from 0 to 7 meters. Just in case, these are just assumed values. These numbers can be anything. So if I integrate like with respect to x, with respect to y, and with respect to z, then I will get the volume of this bigger box. So this is just the geometrical meaning of dv, or the volume element, that dv is a small piece of volume, a small chunk of volume inside a bigger body. Um, so this was for the calculation for the volume of the box. I can, especially in calculus, this volume integration is called a triple integral, and this is used to find the volume of the surfaces of revolution. So we will not be concerned with that in our physics course, but this is really an interesting topic in mathematics, where you can find the volume of the different surfaces of revolution by using this triple integration or the volume element. So this was the physical or geometrical meaning of this volume element in rectangular coordinate system. Similarly, if we are in a spherical coordinate system, so in that we have in spherical coordinate system, we have r, theta, and phi instead of x, y, z. We will discuss this coordinate system, or in fact, we will discuss the curvilinear coordinate system in greater detail in our upcoming lectures, and then we will deal this as a special case of those curvilinear coordinates. But I assume that you know the basics of the spherical coordinates, and this is the value of the volume element in the spherical coordinates. Now, as in the case of the rectangular coordinates, that dv represent the volume, the volume of this small box. Similarly, this dv in spherical coordinates here, d tau, some authors use d tau for it. So d tau or dv gives the volume of a small chunk inside a spherical object. For example, here, uh, I have taken this piece. Let's suppose or assume that um, this is a slice taken from a spherical watermelon. So what is the volume of this shaded region, like this red, blue, and black shaded region? This volume is represented by d tau or dv, and this is the volume element in spherical coordinate system. Now, in this direction, this is d theta, this red curve. This black curve, when I go outward, radially outward, this is dr, this is d theta, and that's d phi. So the product of these three, like as in this case, dx into dy into dz, gives the volume of this small box. Similarly, the product of these three lengths, dr, d phi, and d theta. In fact, this is not a length, d theta is not a length, and d phi is not a length. We have to multiply with, these are dimensionless numbers. So we have to multiply with something having the dimensions of length. So in short, the volume element in spherical coordinates is given by this BLR, the small length in the r direction is given by dr, the small length in the theta direction is given by r d theta, and the small length in the phi direction is given by r sine theta d phi. So when we multiply these three quantities, these are just scalar numbers. So we will get this as a volume element. And this volume element represents a small piece of volume inside a spherical object. Now, if we integrate this over the whole sphere, then we will get the volume of the sphere. We will do in one of our problems in this lecture. This is actually coming in the next slide. So the summary of this slide is that the volume element gives us the volume of a small piece inside a bigger object. Like in rectangular coordinate system, the volume element is a small cubical box. And in spherical coordinates, the volume element is a small chunk of spherical object inside the huge or the bigger spherical body. So this is the bottom line, that you have just to remember this value for the rest of the lecture, that the volume element in spherical coordinate is given by this ugly looking equation. And it's really easy in this rectangular coordinate system. Uh, our first problem is very easy. We are asked to find the volume of a sphere. Now we are going to find the volume of a sphere as we discussed in this slide, that the volume element in spherical coordinate is given by this expression. So if I'm interested in finding the volume of a sphere, I have to integrate this expression. But what will be the limit of integration? Well, the limits are well known to us from the spherical coordinates. The limit on r is from 0 to infinity actually. But if we are going to find the volume of a sphere of some radius r, then we have to integrate from 0 to r, not from 0 to infinity. Then the general limit for theta are from 0 to pi. This is the pi angle, and this can go till this level. So the limit on theta is 0 to pi. Like this theta is the angle with z axis. So this is positive z axis, and below this origin there will be negative z axis. So if I start this angle from the positive z axis, then it can go and it can stop here at the negative z axis. So this whole limit of theta is pi. Similarly, sorry, not pi, this is the limit of theta. So the limit of theta is 0 to 0 to pi. Similarly, we have the limit for phi, and phi is the angle in this xy plane, and this angle starts at x um, at x-axis, and then it goes around the whole circle, and then it stops at this x again. So the limit of phi is actually 0 to 2 pi. So if we integrate this volume element, This volume element represents a small piece of a small chunk of spherical object. So if I integrate this over the whole sphere, then I should get the volume of the sphere. And this is exactly what I'll do in this problem. So the problem is that find the volume of the sphere. Now, this problem is extremely easy. Just I have to integrate the volume element. So uh, and this is given to us that the sphere has a radius r. So I need to just integrate the limit for the r will be for r variable will be from 0 to r, the limit for theta r from 0 to pi, and the limit for the limit for phi from 0 to r from 0 to 2 pi. So this is just a triple integral. Now, to perform integration with respect to let's separate these integrals. These are just scalar integrations. So in this steps, I'm writing the r integral separately. So this is r squared dr, and this the limit of integration is from 0 to r because our sphere has a radius r. Naturally or generally, the limits for the r are from 0 to infinity. But in this case, as I mentioned earlier, that the sphere has a radius r, so I have to integrate from 0 to r. So this is the r integral. Similarly, this bracket is the theta integral, and I have to integrate from 0 to pi. And the integration of sine theta is very simple. It's just cosine theta, and it is just from 0 to pi. Similarly, this is the pi integral, and the limits are from 0 to 2 pi, as I discussed, and we'll discuss this later in this course as well. So these integrals are really simple. This integral will give me r3 by 3. And when I put this limit, like for r, I'll put capital R and the other limit is 0, I'll get this term, r3 by 3. When I do this integration, I'll get cosine theta. And when I apply the limit, so I'll get 2 from here. From this bracket, I'll get 2. You can verify this, it's very simple. Similarly, this integral is extremely easy. Just it will give me phi, and the limit are from 2 pi to 0. So I'll get this just 2 pi number. And when you multiply these three numbers, you'll get this 4 by 3 pi r cube. And this is the famous equation for the volume of the sphere. So we easily got this expression by integrating the volume element in the spherical coordinate. As I mentioned earlier, that the volume element is the volume of this that smaller chunk inside the spherical object, and integrating it over the whole sphere will give me the volume of the sphere, and it did. Our next problem is that uh, a charge density is given to us. So let the charge density on a sphere is given by this expression, where k is a constant, and this charge density is a function of r. Like we have charge on the surface inside a solid sphere, and the charge increases as we go from the center of the sphere, and it increases linearly with r. So, for example, the charge density at the center where r is 0. But as we go away from the center of the sphere, the charge on the body increases. The charge density actually increases. So we are asked to find the total charge on the body. Now, this is a classic problem in electrodynamics, and most of the time the charge density will be given to you, usually the charge per unit volume. So in that case, if the charge density is given in spherical coordinates and the body is spherical in shape, so it's better to use volume element in spherical coordinates. So we'll do this in spherical coordinates. So this is our scalar function k of r, and the volume element in spherical coordinates is given by this expression. And again, here we are asked to find the charge on a sphere having radius r. So our limits on the r integral will be from 0 to r, not 0 to infinity, as the general limits are from 0 to infinity. But in this special case, the sphere has a radius r, so we'll integrate from 0 to r. So what we'll do, we'll take the volume element, we'll put the volume element in spherical coordinates over here, and then we'll take the charge density as is given. So we'll put it here. And as it's given that k is a constant, so we can take it outside of this integration symbol. So put the value of this volume element, put the value of this rho, the charge density. this is charge density Kr, and this expression is this one. This is for the volume element in the spherical coordinates. Now take this K outside of the integration and separate integrations on different variables, like separate the R integral, separate the phi integral, and separate the theta integral. Now look at the charge density is simply R power 1, and we have R in the R square in the volume element. So this R and this R square will make up R3. Now integrating this thing will give me R4 by 4. And when I put the limit uh, from 0 to R, I'll get uh, capital R4 by 4. Similarly, integrating this term, as in the previous case, will give me just 2 pi. And integrating this will give me just 2 as a number. So when I multiply all these things, all these numbers, then my final answer will be 4, sorry, not 4, pi, k, and R4. So this is the total charge. And when you look this thing physically, this is charge density. Charge density is charge per unit volume. So this is actually, this rho is charge divided by volume. So its unit are coulomb per meter cube. And I have a meter cube here or a volume here. So when I integrate it, the charge density or charge per unit volume over the whole volume, the volume will cancel out in terms of units, and I'll get the charge. So this is the total charge on this sphere. Now, this is a simple relationship for a charge density, like just a linear relationship. So in most of electrodynamics problem, this charge density will be given to you as a function of R. Uh, uh, if the charge density only depends on R, then it's spherically symmetric. But there are cases where the charge density can depend on theta and phi. So then this whole function will be a function of R, theta, and phi. And then these integrals, they may become a little complicated, like this. If I have a pi dependence and a theta dependence in this charge density, then those dependencies will go in their respective integrations. And then you have to perform these integration with those functional relationships, and you may get your final charge density. Similarly, this problem, this can be this charge density, if you are working in mechanics, if this is the mass density of an object. So in a similar fashion, you can find the total mass of the body by integrating the mass density over the whole volume. So I hope you got the idea, and you may be able to do these types of simple problems. If this charge density is given to you, or the mass density is given to you, or any scalar function is given to you, and then you will be in a position to integrate in the appropriate coordinate system. So uh, if this scalar function in general, if this scalar function in general is given in rectangular coordinate system, then you have to use the volume element and rectangular coordinate system. If this scalar function is given in spherical coordinate system, then you better use this volume element in the spherical coordinate system. Similarly, if this uh, scalar function is given in cylindrical coordinate system, then you have to use this volume element in cylindrical coordinate system. So this is just a simple exercise to do in different coordinate system. Our last problem is to perform a volume integration for a vector function. For example, we have this f as a vector function, and it's given by 2z minus xj and yk. So this is the x component of this vector field, this is the y component, and this is the z component. And we are asked to find this triple integration, or the volume integral of this vector function over the whole volume. And we are given certain limits. The limits for x are from x equals 0 to x equals 2. For y, we have 0 to 4. And for z, we have the limit x squared to 2. So we have to integrate this vector function given these limits. Now as we discussed in our first slide, we just have to put a vector function here and just put the volume element here. Now you can see that our problem is in rectangular coordinate system. Look at this is a function of x, y, and z, this vector function, and here now it's natural to use the volume element, this dv, and rectangular coordinate system as dx, dy, and dz. And as I mentioned in the first slide, that dv is a scalar quantity, so I do not need to put any dot or cross product here. Now, just put the value of this f and multiply it with the volume element and rectangular coordinate system, and then do this integration. Now, look at the limits. The limits of x and y are pure numbers, like x is from 0 to 2 and y is from 0 to 4. But the limits on z are are given as in the form of x. Our z is a function of x, and in this particular case, z is equal to x square. So when this is the case, when the limits are given in the form of functions, we have to integrate that integral first. For example, here, this z is given in terms of x. So I have to perform this z integral first. So and I'll treat I'll leave the dx and dy. I'll hold them hold these integration for later parts. So first I'll have to integrate with respect to z. So look at, I have to integrate this whole function, this whole bracket, this whole f with respect to z. So look at here, I have z. So integrating this with respect to z will give me z square by 2. And z square by 2 will cancel this 2. So I'll get this term, this one. Similarly, here I do not have any z. So integrating this with respect to z will just give me a z, which is just here. And then here again, we do not have any z. So integrating this with respect to z will give me just z. Now, what are the limits on z? Now, in this step, this integration with respect to z is performed, and the limits are from x squared to 2. Now, whenever there is z, I have to use these limits for z. So in this step, here integration is performed, and we have to put these limits. So when you put these limits, you will end up with this expression, this bigger bracket. And now you can clearly see that this is just a function of x and y, because z was given to us in terms of x square. And for this x, we used these limits in the form of x. So now you can see that this z square is kind of replaced by x power 4, because z power 1 is just x square, and z square will become equal to z x4. So the bottom line is that this integral is now an x and y in x and y variables, and the limits for x and y are very simple. So now we have to perform this integration with respect to y. Now there's no y here, no y here, a y here, no y here, no y here, and a y here. So integrating this with respect to y will just give me 4y, this here. Similarly, there is no y here, so integrating this with respect to with respect to y will give me just y, because the integral of dy is simply y. Similarly, I have a y here, so integrating this with respect to y will give me y square by 2, and this 2 will cancel with this 2, and I'll simply be left with this y square, with this k unit vector. But one thing I did not mention, please note that I, j, and k unit vectors are constant. So you do not need, so you can easily pull them out of the integral symbol. As we discussed in our first lectures, then that in rectangular coordinate system, the unit vectors are constant. So we can clearly take them outside of the integration symbol. But these unit vectors are not constant for the case of spherical coordinates. So be careful when you are performing a vector volume integral. You cannot remove those out of the integration symbol because they are not constant. Now, so performing this integration with respect to y, this will give us this quantity. And the limit for y are from 0 to 4. Now, I'm leaving you this simple step to verify uh, that just put the limits, and whenever there is y, just put 4 and 0 for those values and simplify. So putting this limit will will remove this y from this bigger expression, and our function will be left with only in x, and then we will integrate with respect to x, and then that will be the end of this process. So when you put limits in that expression, the final form of the result is given by this uh, this bracketed expression. Now our last integration is with respect to x, and we have to integrate 16 with respect to x. So this will just give me 16x, because I have to multiply this dx with everything. So this will become 16 dx, this will be become minus 8x dx, this will be 16 dx, this will be 4x4 dx, this will become 4x3 dx, and this will be minus x squared dx. So this dx will be distributed with every term, and then I have to integrate from 0 to 2. So integrating this with respect to x will give me just x, and this will give me x squared by 2, and that 2 will make this 4. So this is minus 4x squared. Similarly, this is just 16, so integrating this with respect to x will give me just x. Now this is x power 4. Integrating this with respect to x will give me x5 by 5. So this is x5 by 5, and this is well, this 4 coefficient. Uh, Integrating this with respect to x will give me x 4 by 4, and that 4 will cancel this 4, so I'll be left with this x to the 4 alone. And then integrating this with respect to x will give me x3 over 3 with this 8 up front. Now in the last, I have to use these limits from 0 to 2, and whenever when I put these limit and I simplify, so look at, I have to now use the idea of vectors. I have to collect like terms, like those uh, mm, I'll add I components, j components, and k components. So here I have an I component, I have an I component here. I'll add these two. Similarly, I have a j here and I have a j here. So this is plus 16j and that's minus 16j, so they'll cancel. And similarly, I have a k unit vector here and k unit vector here, and then I have to add these two. So when I do this simplification, this will be my final answer. And clearly, it's a vector quantity, because look at here, I was integrating uh, a vector field or a vector quantity over, over the volume. So my final answer must be a vector, because look at this expression. This is a vector quantity and this is a scalar quantity. So the ultimate answer will be a vector quantity. So this was an example of a vector volume integration, and the previous two examples, this one and this one, these were the scalar volume integration. So with this, I'm going to end this lesson. And if you have any question, I'll upload this video to you, and then please watch it carefully. Try these exercises and these problems by your own. And if you have any question, please email me. Thank you.